Welcome back to NCERT material. In this video, we're doing a complete revision of Class 12 Physics, Chapter 3, Current Electricity. We'll cover everything from electric current and drift velocity, all the way to Kirchhoff's laws, the Wheatstone bridge, and superconductivity. Grab your notebook, and let's get started. Here's a quick look at everything we're covering today. We'll start with the basics of electric current and drift velocity, then move into Ohm's law and resistance. After that, we'll look at combining resistors in series and parallel, understand cells and their internal resistance, apply Kirchhoff's laws, explore measuring instruments like the galvanometer and potentiometer, and finish with the heating effect, electric power, and superconductivity. Let's dive right in. Let's begin with Section 1. Electric current and drift velocity. So, what exactly is electric current? Electric current is simply the rate at which charge flows past a cross-section of a conductor. By convention, we take the direction of current as the direction in which positive charge would move. Now here's something interesting. Even though current has a direction, it is still treated as a scalar quantity. That means currents add up using ordinary addition, not vector addition. So the angle between two wires carrying current never affects the total current in a circuit. The formula is simple. Current equals charge Q divided by time t, or in calculus form, dQ by dt. Now, who actually carries this current? It depends on the medium. In solids, like metal wires, free electrons, also called valence electrons, drift through the material and are the only current carriers. In liquids, such as electrolytes, both positive and negative ions are free to move, so both contribute to the current. And in gases, which are normally insulators, current only flows once the gas gets ionized at low pressure, then both ions and free electrons carry the charge. Let's talk about drift velocity. Inside a metal, free electrons are actually moving all the time, but randomly, in every possible direction, due to thermal energy. If you average out all of these random velocities, they cancel out to zero. So even though the electrons are buzzing around like crazy, there's no net flow of charge, and hence, no current. But the moment you apply an external electric field, every single electron gets an extra nudge towards the positive end. That small, extra, directional push is what we call drift velocity. Here's a fact that surprises most students. The drift velocity of electrons is incredibly slow, of the order of just 10 to the power minus 4 meters per second. And the relaxation time, which is the average time between two collisions of an electron with the lattice, is about 10 to the power minus 14 seconds. So then why does your bulb light up instantly when you flip the switch? Because it's not the electrons themselves that need to travel, it's the electric field that gets established almost at the speed of light. And with such a massive number of free electrons in the conductor, even this tiny drift velocity produces a large, usable current. Next, let's understand mobility. Mobility tells us how easily a charge carrier drifts when an electric field is applied. Formally, it's the drift velocity produced per unit electric field. So if a material has higher mobility, the same electric field will push its charge carriers faster, resulting in a bigger current. The formula is mu equals Vd divided by E, which also equals Q tau over M, and its SI unit is meter squared per volt per second. Now let's connect the microscopic and macroscopic pictures. The current I flowing through a conductor can be written as equals N, A, E, Vd, where N is the number of free electrons per unit volume, A is the cross-sectional area, E is the charge on an electron, and Vd is the drift velocity. This single equation is powerful because it links the drifting electrons we just discussed to the current you actually measure with an ammeter. And if you substitute the expression for drift velocity into this formula, you arrive at the microscopic explanation of Ohm's law, which is exactly where we're headed next.